So good afternoon, everybody. This is just a second. As you can see from the subtitle, I'm going to be talking about what a second is, what can happen in 1 second, and why we need leap seconds. Firstly, before I get stuck into the talk itself, there's a number for you. 17,107,200 seconds. Does that length of time mean anything to anybody? Can you visualize, can you think about what 17 million and a bit seconds actually corresponds to? We don't tend to think of time extended in terms of seconds. We tend to think of minutes, hours, days, months, years. But this is just a way of thinking about what a second actually is. 17.1 million seconds is the length of time between now and when the UK went into COVID lockdown at the end of March. So we've been in a state of lockdown, partial or complete, depending on where you are in the UK, for about 17 million seconds. That either might sound like a lot or it might sound very short. That depends partly on your perception of how the lockdown has gone and partly in your perception of what a second is. So that's just a reminder that 17 million seconds is either a very long time or a very short time, depending, of course, on the context. So I'm going to be talking about how motion defines time. We can't measure time independently of motion. I'm going to talk about the definition of a second, what can happen in 1 second to give us a little bit of context. And I'll be talking about how the rotation of the Earth is slowing down, why it's slowing down, and what the consequences of that slowdown are. And I'll finish with the need for leap seconds. So how do we think about time? Well, as I say, it's tempting to think about time completely independently of space, but actually you can't measure the passage of time without something usually moving through space. That's the way we conventionally measure time. So for instance, if we look back to millennia past, the time has been measured by the motion of astronomical objects. For instance, the motion of the sun in the sky, or perhaps I should say the apparent motion of the sun in the sky because of the rotation of the Earth. The sun moves across the sky, and if we have something like a sundial, we can cast a shadow, and then we can get an idea of how the time of day progresses by looking at the shadow on the sundial. For slightly longer times, we might use the phases of the moon to judge the passage of time. So astronomically speaking, timekeeping has been with us for many, many millennia. But if we ask ourselves what is a second, then perhaps we come to the conclusion, well, surely that's trivial. The Earth spins on its axis once a day. And so surely that means that if we know a day is 24 hours, then an hour is split into 60 minutes and a minute is split into 60 seconds. So we know that 1 second is that fraction of a day, 24 by 60 by 60. If we multiply those numbers out, we find that 1 second is that particular fraction of a day, 1 over 86,400. Simples. That number, by the way, 86,400, will keep cropping up in this talk. So I'll be bumping into it from time to time, and it's simply 24 times 60 times 60. So if that's all there is to a second, it's simply that fraction of a day, then that's the end of the talk. Well, yeah, you wish. No, it's not the end of the talk. This talk is going to continue for another 2,000 seconds or so. So let's look at how the Earth actually moves. The Earth orbits the sun in an ellipse, and that means the Earth's speed around the sun in its orbit depends on its distance from the sun. So according to Kepler, who worked this out a few hundred years ago, the Earth sweeps out, if you like, an equal area in an equal time. So in other words, when the planet Earth is close to the sun, as on the left-hand side, in 1 month it goes around quite a large arc of its orbit, compared to when the Earth on the other side here on the right-hand side, when the Earth is a long way from the sun, in that same time period of 1 month, it only sweeps out a relatively small arc. So these blue areas are the same regardless of where the Earth is in its orbit. And that means, as you can see, it covers a lot of ground on the left-hand side in terms of its orbit and a smaller amount on the right-hand side. The Earth's orbit around the sun varies throughout the year. And that is one of the reasons, that's the prime reason why if we use a sundial to say, where is the sun in the sky, let's cast a shadow, we don't necessarily get the time we expect because it depends on where the Earth is in its orbit around the sun. At different times of year, the Earth will be traveling at different speeds. And we can see this if we photograph the sun at the same time of day throughout the year. This particular photo was taken, I think, an image of the sun was taken something like every 10 days throughout a year. And this particular pattern is called an analemma. So we get a variation. We can see the north-south variation. We know that the sun is higher in the sky in terms of altitude. The sun is higher in the sky in summer in the northern hemisphere and lower in the sky in winter. And that's a result of the 23 degrees tilt of the Earth's axis. So in the northern hemisphere where this particular image was taken, then the position for June is at the top of the image and the position for December is at the bottom of the image. So it's no surprise to find that the sun appears at different altitudes in the sky at different times of year. But what is a little more surprising perhaps is that we don't simply get a vertical line of dots. If we take the picture at the same time, for instance, noon, 12 o'clock every day, let's forget the fact that the clocks jump forward for half the year. If we just take, let's say, universal time, if we were on the Greenwich meridian, if we were to photograph the sun every day at the same time, we would find not only we get this north-south variation, we also get a variation east-west. In other words, at the same time of day, in some parts of the year, the sun won't quite have reached the meridian, the north-south line, cutting through our particular position. In some days, the sun won't have reached that point and it will arrive a bit late. And on other days of the year, the sun will go past the meridian and at noon, it'll be a little bit the other side. Not a huge variation, but the variation can be up to 15 minutes either way in terms of where you would expect the sun to be crossing your meridian. So that figure of 8 pattern, that so-called analemma, would be the same sort of image. It wouldn't be quite the same shape taken from different latitudes, but you will always find this north-south variation because of the tilt of the Earth, and you will always get this east-west variation because of the Earth's rotation around in its orbit around the sun. So because of that elliptical orbit, we get this variation, and that's precisely why sundials don't read accurately. It's because of the Earth's orbit. The 15 minutes either way is because of the way the Earth's velocity changes as a function of time. It's nothing to do with the fact that the Earth's axial rotation changes. It's purely because of the Earth's orbit. If we wanted to know how the Earth spins in terms of how long does it take the Earth to revolve once, then we need something far more accurate than a sundial because of the reasons I've just said. The sundial is affected by the Earth's motion around the sun, not simply the Earth spinning on its axis. So if we want to know the length of a day, we need something much more precise than a sundial. And when I'm talking here about the length of the day, I'm not talking about the length of daylight. I'm not the time period between sunrise and sunset. I'm talking about what is the length for one rotation period of the Earth relative to the sun. So we need something more precise than a sundial. And in 1968, the second has had a very precise definition. The second has been defined as that many oscillations, 9 billion and change, 9 billion oscillations of a cesium atom are defined to be 1 second. Well, actually, it's the microwave radiation corresponding to electrons jumping around in this particular atom, an isotope of cesium called cesium-133. That has been the definition of atomic second, and hence atomic time, since 1968. And this is called the cesium standard. We've been using it for more than 50 years now. And there's one of the early atomic clocks. I won't talk you through exactly what's going on there, but it involves a small number of cesium atoms, and microwaves are being absorbed and emitted by those atoms. And by measuring the frequency of those microwaves, we can get a very accurate indication of a second, simply by counting, if you like, until we reach 9 billion, 192 million, etc. That tells us 1 second of time has passed. Atomic clocks are accurate to a precision of something of order a nanosecond per day. And if you let the atomic clock run, one run. 1 nanosecond per day accumulates, but there tends to be a little bit of averaging. And that means that it's actually over a long period of time expected to be equivalent to a drift of something like 1 second in 30 million years. So that's the sort of precision we can obtain with atomic clocks. The picture I showed was one of the early atomic clocks. Nowadays, they are getting smaller and smaller, and NASA is now developing a so-called deep space atomic clock that is about the size of a toaster. It's not the whole thing, it's just this little box on the top that these particular technicians are dealing with in order to put an atomic clock into what I presume is a satellite here, a satellite or a space probe of some kind. So by putting accurate atomic clocks inside a space probe, it will improve the navigation in principle. If the probe knows exactly how much time has elapsed since it's launched, then it's got a pretty good idea of where it is, using its own internal inertial navigation and this very accurate clock, which hopefully won't drift over the years or perhaps decades of the lifetime of the particular space probe being put together here. Time really does matter because, for instance, if we look at how time affects one of the modern day necessities, a GPS system, global positioning system, relies on calculating how long the light signal or the radio signal has taken from a satellite to reach you. There are 24 of these satellites buzzing around the Earth, as indicated by this little graphic on the right-hand side. And if at a particular point on the Earth you can get a signal from various satellites, if you can time how long it's taken for the signal from the satellite to reach you, then you can work out your position on Earth. But it relies on knowing the time in each of these satellites. Each satellite carries an atomic clock on board. If one of those clocks was wrong by, let's say, hypothetically, 1/1000th of a second, if it was wrong by a millisecond, then the distance you calculate, how far does light travel in 1 millisecond, your position could be wrong by 300 kilometers. And if the clock on one of these satellites was wrong by a microsecond, so now we're talking how far does light go in 1/1,000,000th of a second, you could be getting your position wrong by 300 meters. So you can see that if your clock was wrong by only a few nanoseconds, you would still be wrong by a few meters. And ultimately, that's what determines the accuracy of GPS positioning systems, is how accurately you can get all of the clocks in all of these satellites to synchronize. So absolutely, time accuracy does matter. If we want to work out which continent we're on, then it doesn't matter if the clocks are slightly wrong. But if we want to work out which lane of the motorway we're driving down and when the next exit is going to be, we need time accuracy of order nanoseconds. And for that reason, GPS clocks in all of the satellites in the GPS network are resynchronized with each other. Well, technically they're resynchronized with a particular ground station. They're resynchronized every few hours, if possible, to eliminate the sort of drift that would otherwise occur. A satellite should be good for quite a few days, possibly even a week or two on its own, but they're resynchronized as often as possible to keep all of the GPS network synchronized with each other. And then you get maximum accuracy of the GPS system. If we ask ourselves what can happen in a computer, not necessarily the computer that you're staring at the moment, whether it be a desktop machine or an iPad or something else, but if we ask ourselves what can the fastest supercomputers do, well, they can do an awful lot of calculations a second. Not this number in red at the top, 200 billion, that would be very pedestrian. I need to add a few zeros and an extra 3 zeros, well, that's not quite enough either. There we go. That's the actual number of calculations that can be done by the world's fastest computer at the moment, which I believe, last time I checked a few months ago, was this computer sitting on the left-hand side there, the so-called IBM Summit. So it can do 200,000 million calculations per second. And that might sound like an awful lot, but even with that amount of speed, running, for instance, a very complicated program, a very complicated simulation of the early universe, to take one example, that particular simulation to calculate what is happening as the universe collapses and galaxies form, that calculation might take days or weeks or even months of supercomputer crunching time. And at that many calculations per second, you can see it's a huge number of calculations that are required in some of the more complex simulations that are done, either of the early universe or the way proteins interact, or various other simulations that involve huge amounts of computing power. So even the computer in front of you can probably do 1 billion calculations a second, even if it's a humble iPhone or iPad, or other makes are available. But even something as mundane as a phone is capable of doing something like 1 billion calculations per second. And so we scale that up when we talk about these large-scale supercomputers that exist around the world. But if we ask ourselves, well, we know the speed of light is very fast, so we can ask ourselves, how far can light travel in 1 second? Well, we know that's a fairly large value, 186,000 miles, to use the old imperial units, 300,000 kilometers, a nice round number when you talk about the metric equivalent. And in terms of objects that we have produced and thrown off the Earth and out into the solar system, 2 of the fastest objects are the Voyager probes that were built in the 1970s and launched in the late 70s. They are both leaving the solar system, Voyager 1 and Voyager 2. They're heading off in different directions, but they're both traveling at about 16 kilometers a second. Very fast for an Earth-based object, but clearly very slow compared to the speed of light. So if we wanted to send a probe out to the nearest star, that sort of speed would mean it would take an awful long time to get there. If we think of more mundane things on the Earth in terms of our daily lives and what can happen in 1 second, we can ask ourselves, well, what happens, for instance, on the internet in 1 second? Taking data from last year, we can calculate that in 1 second, for essentially every second of last year, 300,000 texts were sent by the SMS system. And something of order 60,000 searches were made in every second. According to Google, other search engines are available. And in terms of video, something like YouTube, or again, other web servers are available, other video servers, something like 75,000 videos were downloaded every second. I believe at least half of them involves cats, but I don't actually know about that. I haven't got the data to hand. Of order 700,000 messages were sent every second via apps such as WhatsApp or other messaging applications. And one of the most staggering results is the number of emails that were sent every second, approximately 3 million emails per second every second of last year. If you update that for 2020, the stats aren't in, but I would imagine that for 2020, even in the non-COVID times of 2020, the stats for this year must be up on these numbers from last year. So it just reminds us that 1 second is, in some sense, a very long time, both in terms of how much you can calculate on a supercomputer in 1 second, but also what is going on in the world in terms of people communicating with each other. In every second, there are millions and millions of interactions between various users on planet Earth. If we apply atomic clocks to what's going on with the Earth, we find that the Earth is slowing down. We've had atomic clocks for 50 years. So we've had plenty of time to watch what happens and record what the Earth's rotation is doing. And we find that on average, the Earth is slowing down. Not necessarily in the last few years or the last few decades, but it's no surprise to find that the Earth has been slowing down over a long, long period. Back in 1968, when atomic time was instigated, a second was defined as the number of oscillations of cesium that I told you, the 9 billion or so oscillations of the cesium atom. That number was chosen in order that 86,400 seconds was precisely how long it took the Earth to revolve once relative to the Sun. In other words, the second was defined in 1968 such that the day was exactly 24 hours long, 24 hours, or if you prefer, 86,400 seconds. But the Earth has been slowing down, and for 50 years since atomic time was instigated, there's been variations, but as of now, compared to 1968, the day is a little bit longer. Not by much, but it is definitely longer. Instead of the day being 86,400 seconds, the day is now 86,400.001 seconds. The day is now 1 millisecond longer than it was when we started atomic time. Why should that be? Well, the reason for that started 4.5 billion years ago. So what we think happened in the early stages of the formation of the solar system is that the primordial Earth was struck by an object about the size of Mars. We call it Theia, and this is the theory that seems to be reasonably well established and reasonably well accepted, that this is how the moon formed. The Earth was struck by an object, and as you can see from this artist's impression, a huge amount of material was spalled off the Earth, and that eventually condensed into what we now call the moon. How fast was the Earth turning on its axis back then? Well, we have no idea, because whatever the rotation period of the Earth was, it would have been changed by this enormous impact of this other celestial body. It took the Earth a little while to recover, and eventually the spalled material condensed into the moon. Once the Earth recovered from this impact, it's thought that its rotation period was about 1 revolution in 5 hours. And ever since then, for the past 4.5 billion years, the Earth has been slowing down from its initial 5-hour rotation period. Why should the Earth be slowing down over that time? Well, it's because of the moon. The moon that was generated by that same impact has been slowing the Earth down ever since. The moon here on the right raises tides on the Earth. There's a tidal bulge facing the moon and a tidal bulge on the other side of the Earth. But notice these bulges don't quite line up with the moon, because the Earth is rotating and effectively dragging all the water around with it. And therefore the tidal bulge of water produced by the moon that we can see here is a few degrees ahead of where the moon is actually pulling on the Earth. So when the moon pulls on this bulge, which it does a little bit more strongly than the bulge on the other side, when the moon pulls on this, it's effectively applying a braking mechanism to the rotation of the Earth. So over billions of years, the Earth has been slowed down because the moon has been pulling on that tidal bulge, which has been raised by the moon itself. And that will continue for as long as the Earth is rotating faster than the moon is going around the Earth. The Earth is currently rotating once in approximately 24 hours, but of course the moon is going around the Earth approximately once a month, once every 28 days or so. And so the tidal bulge is getting pulled in this direction. If the Earth ever slows down to the point where the Earth is rotating at the same rate once in a particular time period, which is the same as the time period for the moon going around the Earth, then that bulge will be facing the moon, and the Earth and the moon will be tidally locked to each other. So at the moment, the moon, the one face of the moon, is always facing the Earth. We always see, remember, the near side of the moon, which is always the same face. The far side of the moon, regardless of whether it's lit or unlit, whether it's the dark side or the light side, the far side of the moon is something we can only see by sending satellites around the back of the moon. The near side of the moon always faces the Earth. Eventually, because of this effect of the moon slowing the Earth down, eventually the Earth's rotation will synchronize with the moon's orbit, and then the same side of the Earth will always face the moon, just like the same side of the moon currently always faces the Earth. So not only will we always see the same face of the moon, it means only half of the Earth will ever see the moon. The other half of the moon, the other half of the Earth will always be on the other side, and the moon will never rise as seen from that part of the Earth. That won't happen for quite a long time. I'm not sure how many billion years it will take before eventually the Earth and the moon are tidally locked together. But effectively, the moon is robbing some angular momentum from the Earth's rotation. The Earth is losing some angular momentum, and the moon is gaining some. That is why the Earth is slowing down. So what? Why does it matter that the Earth is slowing down? So a day is no longer an exact number of seconds. It used to be, but it is no longer an exact number of seconds. So what? Well, it's just like the problem we have with days and years. A year is not an exact number of days. What do we do about that? Well, if a year is this particular number, 365.2422, and a few more decimal places, let's just round it there for the time being. If a year is this many days, then if that was not addressed, then the calendar would drift relative to the seasons. Instead of the 1st of January always being in the middle of northern winter, it would slowly drift and eventually it would be in the summer after a long enough period of time. So we get around that problem by inserting an extra day, a so-called leap day, and we do that every 4th year. That would make the calendar year 365 and a quarter, in other words, 365.25 days, if we inserted one extra leap day every 4 years. You can see that that's close, but not quite the same as the actual number of days in a year, 365.2422. So it's good in that it corrects for most of the problem. It's still not quite right. We would still have a problem with the calendar drifting relative to the seasons if we waited long enough. And so the solution was to say, well as it inserting a leap day every 4th year, let's have another rule. And the rule is we'll skip a leap day in a century year that's not divisible by 400. And that gives us 365.2425. In other words, it gets very close to the actual number of days in a year. So having this leap day every 4 years and having this extra rule for centuries means that we are very close to correcting for the number of days in a year, and it keeps the calendar and the seasons synchronized. It keeps them synchronized such that we don't have to worry about this for thousands of years. In other words, the calendar and the seasons are not going to drift relative to each other for tens or hundreds of thousands of years. It is no longer a problem if we stick to this rule. So that's great for leap days. It's a rule that we know what's going to go on. We can predict when a leap day is needed, and we can predict that years, decades, centuries, thousands of years ahead, we know a leap day is going to be needed. But coming back to the problem of the Earth's rotation, if we want our 24-hour clocks to be synchronized with the rotation of the Earth, why do we want that? Well, we would prefer the sun to be in the sky when our clocks say it's daytime, just like we don't want the calendar to drift relative to the seasons, which is an orbital problem. For the Earth's rotation, we don't want our clocks to start drifting with what the sun is doing. We don't want the sun to be in the sky when our clocks say it's noon, and then sometime later, the sun to be set when our clocks say it's noon. We prefer to keep them synchronized. And that, analogous to why we need leap days, means that we need leap seconds inserted into our clocks every once in a while to keep the Earth's rotation synchronized with our clocks. Well, strictly speaking, we don't absolutely need to do that. We could just say, well, the Earth is slowing down, so the days are getting longer. Well, let's just let the seconds get longer. Why don't we just keep the definition that a day is 86,400 seconds? And if the Earth slows down, well, the seconds get longer. We could indeed do that, but the scientists would be furious if we did that, because it would mean that we have to keep resetting our clocks over and over and over again. As the Earth slowed down, we would have to keep redefining what we mean by a second, because a second would keep getting longer and longer and longer over periods of years, decades, hundreds of years, and millennia. So it would be totally impractical to keep redefining what we mean by a second. So we're not going to have that option. So the option is either we let the clocks drift, or we add a leap second every once in a while. And the problem is, how often do we need to introduce a leap second? So let's look at this plot. Here on the horizontal axis, we have the date for the last 5 decades or so. And what we're plotting here in the black line, ignore this gray line for the moment. In this black line, we're plotting the length of the day minus 86,400 seconds. So it's this extra bit since atomic time was first introduced. And what we found is the length of the day. Here we see vertically here in milliseconds, so it's not a great increase, but it's definitely measurable. The length of the day has been varying quite substantially for the past 50 years. It hasn't simply been increasing, which is what we would expect from what the moon is doing. So there must be some other effect, which is making the Earth's day change year on year, decade on decade. We can see the variation is there's a long-term variation, there's a very spiky variation there, and there's a few little bumps as well. This black line that goes down the middle, which I hope you can see, is a sort of average of all this spiky year-on-year variation. If you look where these spikes are, perhaps you can see that they are absolutely 1 year apart. So these spikes here that you can see are annual variations. They are year-on-year variations, summer to winter to summer to winter. There seems to be a variation in the rotation of the Earth. There are a few other bumps in there as well, which are thought to be due to the Earth rearranging its continental plates. In other words, earthquakes make things rearrange themselves a little bit. But we can at least say this variation that we see, summer to winter to summer to winter, we have got an idea of what's going on there, because this is related to the way the atmosphere of the Earth changes. Summer and winter are, of course, related to the tilt of the Earth. In northern hemisphere summer, the northern hemisphere is tilted towards the sun, and in the opposite way round for the winter, where the southern hemisphere is tilted towards the sun. So what that means is the amount of the sun's radiation on the various continents of the Earth changes, and hence the atmospheric circulation, the primary circulation in winds. Some of them actually change direction. In some cases, the primary direction of a wind might be east to west, but seasonally, if you look 6 months later, it might be west to east. So the atmosphere of the Earth carries a certain amount of angular momentum, and if that changes between winter and summer and the northern and the southern hemispheres, that means the angular momentum of the atmosphere is changing slightly, and that means the angular momentum of the Earth changes, which means the length of time it takes to do one revolution will vary. So this variation that we see between summer and winter as we go through the decades, we can understand that in terms of what the Earth's atmosphere is doing. But the elephant in the room is, well, okay, that's the spikiness, but why is it changing like that? Why isn't it just uniformly increasing because of the tug of the moon making the Earth slow down? Well, the embarrassing answer is I can't find that out. I've been trying to find any explanation of why the Earth's rotation has been varying like that. But as far as I can tell, geophysicists don't really understand why it is that during the 1970s, the Earth's rotation period was about 3 milliseconds longer than 86,400 seconds. Whereas in the noughties, 2005, say, it looks like the Earth's rotation period has speeded up a little bit, and the period was now much closer to 24 hours. What is it that's producing this, not year on year, but what's producing this decade by decade variation? I don't think it's very well understood at all, and perhaps we need to take more data. Maybe we need a few more of these variations to see if we can see a pattern. Maybe we just need to keep recording the rotation of the Earth for another 100 years or so, and then we'll have a better idea of what this variation actually is, and then we'll perhaps have a better understanding of explaining what it actually is and what's actually going on. If it's not the atmosphere, then presumably it's something to do with the viscous mantle of the Earth. It might be the core, but I think more likely it's something to do with the way the Earth's mantle is changing and producing these variations. And so combining this data with earthquake data, it might be possible to start understanding what that variation is due to. But if we come back to leap seconds, remember leap days are nice and regular. If we put one in every 4th year, with this caveat that we need to watch out for century years, every 4th year, then we get a very good synchronization between the calendar and the seasons. And it has been agreed that we put it in at the end of February. So February 29th in the standard calendar is where everybody agrees to put the leap day. But what do we do about leap seconds? Leap days are inserted very regularly according to a formula which allows us to work out when the leap days are going to be for the next 10,000 years or so. But with leap seconds, we can't do that because we can't predict what the rotation of the Earth is going to do next. We've seen its variation and we don't understand it, therefore we can't predict it. So with the calendar, it's easy. We have a rule for adding the leap day. But what about leap seconds? Well, that's decided by a body which goes under the wonderful name of the International Earth Rotation Service. I don't know what happens if they ever take a day off. Maybe the Earth stops spinning, I don't know. But these guys at the International Earth Rotation Service decide what the Earth is doing. They monitor the rotation of the Earth with those curves that we've just seen, and they decide whether or not the Earth's time is getting out of sync with the Earth's rotation. And then they decide that we need to insert a leap day. So they decide how often and when a leap second needs to be added. When's the most sensible place to add a leap second into a day? Well, you could say, well, the easiest thing is just pop it in at midnight. Nobody will notice, so that's the easiest thing to do. But before we see where they're popped in, let's just see how often they've been inserted. On the right-hand side here, let me just move my video camera slightly to make sure it's out of the way. On the right-hand side, we can see the scale from 0 to 25 seconds, showing when leap seconds have been added. And let me get back to PowerPoint. Leap seconds were introduced in 1972. It was decided this is the way we're going to synchronize our clocks. And since then, leap seconds have been added according to this particular curve. So what we can see here is that during the 1970s, remember the Earth's rotation was 86,400 seconds plus about 3 milliseconds. It was running quite slow in the 1970s, and hence we needed to add lots of leap seconds to try and keep things synchronized to a 24-hour clock. But notice that when the Earth's rotation decided for some reason or another to come back closer to 24 hours, so for instance around 2000 in the noughties, around about 2005, give or take a few years, the Earth's rotation period was very close to 24 hours. So we didn't need leap seconds then, and hence there's this gap here you can see for the years between about 1999 and what is that, 2006, there were no leap seconds added because they weren't needed. And the Earth then started slowing down a little bit and a few leap seconds have been added. The last leap second to be added was at the end of 2016. And I don't think we've had one since then, because again, if you look at the curve, this only goes to 2019, not 2020, but you can see that the current rotation period of the Earth is not that much larger than 24 hours, and therefore there's no desperate need to add a leap second just at the moment. But the International Earth Rotation Service are going to continue monitoring the Earth, and then they will decide if we need to add another leap second in order to synchronize our clocks again. Well, that's fair enough, but you can see from what's going on for the last few decades, it's very difficult to predict what's going to happen next. It's like looking at stock market prices or something like that. You can see what's happened for the last few decades, but you really can't predict what's going to happen next. From this curve, you can't tell whether in 2020 the Earth will continue speeding up and its rotation period might actually drop below 24 hours, or whether it's going to bounce back up again and then we'll have a rise. So we can't tell what the Earth is going to do next, so we can't tell when the next leap second is due. If we are going to introduce a leap second, we could do it at midnight. So instead of the clock reading 23:59:59 and then clicking over to 0, we could add an extra second by adding one that was defined as 60 rather than 59. So the clock would look a little bit like this if we have no leap second. 59 clicks over to 0 at midnight. That's what normally happens. But if we wanted to add a leap second, then we could do that by changing the clock after 59:59 and changing it such that it reads 59:60. So the time 23:59:60 is a completely valid time, providing there's a leap second in that particular day. Just because it's a valid time doesn't mean there aren't problems. In some computer systems, if you try and tell it that the time now is 23:59:60, it'll sometimes not accept the input. Sometimes the computer will crash if you try and tell it that is the time, even though that's a perfectly legitimate way of describing the time if an extra second has been introduced. As an aside, it also means that if anybody asks you how many seconds are there in a minute, the answer is not 60. The answer is usually 60, but every once in a while, a minute contains 61 seconds. And then you have the problem of, yeah, okay, I'll insert it at midnight, nobody will notice, everything will be fine. But midnight, where? Everybody has a different midnight because of all the time zones around the world. And you could say, well, everybody will simply insert the second at local midnight. So it'll get inserted in Japan at a certain time, and then a few hours later, it'll be inserted into India's clock, and then a few hours later, it'll be inserted into the UK clock, and then a few hours later, it'll be inserted into the United States clocks. But that would mean that clocks would be out of sync throughout the whole day. Globally thinking, clocks would be out of sync. If you don't insert the leap second at exactly the same instant of time, rather than local midnight, the clocks would be off by a fraction of a second. Who cares? Well, if you're trying to deal with global finance, remember, all global finance these days is digital and electronic, so money is being sent backwards and forwards across the world, millisecond by millisecond. So if your clocks are wrong by half a second, are you absolutely sure that the money sent at this instant has been received by the bank at that instant? What happens for the half second when the clocks are not synchronized? Who actually owns that money when they have sent it and they haven't yet received it because their clocks aren't quite synchronized with those clocks? Can a thief come along and take that money away during the time when those clocks don't agree what the time is? It absolutely matters that clocks are synchronized. So you have to agree not to just do it at local midnight, you have to agree to do it at a particular point, such as, for instance, Greenwich Meridian midnight, and then everybody does it at the same time, even if for some people that means doing it in the middle of the afternoon. There is a problem. Some people really don't like leap seconds. This idea of we don't know what the time is going to be next year or the year after, because we're not sure whether or not we're going to be adding a leap second or not. For some people, that is really unacceptable. They prefer to have a regularity like the algorithm that we have for working out leap days. People want to have the same thing for leap seconds. But because we don't understand how the Earth is rotating, we can't do that. So some people really don't like leap seconds. Some computer systems really don't like leap seconds. As I say, some computer systems treat them okay, but if you try and set the clock during a leap second, some computer systems crash. If you want to know the length of time between two specified times, the time on this day and the time on that day, you have to know how many leap seconds have been introduced in between those two time periods. You know what that is for the past, you don't know what it's going to be for the future. So that is a problem. And some companies really don't like leap seconds to the point where they got around the problem. Rather than saying our clocks are going to run for 24 hours, and then when a leap second is due, we're going to add this extra second at the end of the day, some companies have said, we're not going to do it that way. For instance, Google have said, we are not going to add 1 second at the end of the day and have a 61-second minute just before midnight. We are going to add the second drip feed. We're going to add it a little bit at a time. Every second or so, it's going to add a microsecond or two to keep the clocks slow, such that by the end of the day, they've added that extra second. So they do that. They run the clocks at, 0.001% slow for a day. That effectively adds a few microseconds every second, and therefore, in a sense, they've stretched a second such that during that day, they don't have to drop the leap second into the end of the day. Not everybody does it that way, which means Google clocks aren't synchronized with other people's clocks on a leap day, on a day when a leap second is introduced. So that can cause problems in its own right. But Google have done that because they don't like the discontinuity of having to effectively freeze their clocks at the end of the day for 1 second and then restart them again for the start of the next day. The joke is, well, imagine if you did that with a leap day. If you said that's a perfectly sensible way of working, rather than add a leap second, just run your clock slow for a day. Well, what if they did that for leap days? And here's the joke. Why do the clocks say it's 3 a.m.? Well, adding an extra day to the end of February causes too many glitches. Instead, we're running our clocks 3% slow during February to avoid the irregularity. Rather than add the 29th of February at the end of the month, we're just going to run our clock slow by 3%, and that will add the extra day by the time you get to the end of the month. So there's the joke, the idea that Google has expanded their idea of leap second smearing and adding a little bit throughout the day to cover leap days as well. Okay, no one is going to do that, so that is the joke effectively. But leap day smearing is a joke, but leap seconds are absolutely serious. How do we deal with leap seconds? We don't want to let our clocks run slow continuously and redefine the second when the Earth decides it wants to speed up or slow down. Are we going to keep our clocks synchronized to the sun, or are we going to forget it? Just forget the sun, let atomic time define time, and don't bother with leap seconds at all, and eventually the clocks will be desynchronized to the sun. Who cares? That's going to happen years and years and years into the future. Let somebody else deal with it. Either that, or we do agree to add leap seconds, but when? Are we going to continue to add leap seconds ad hoc as and when the Earth indicates that it needs to? Are we going to add a leap second every year or two and then not add leap seconds for a few years because we don't need them, and then add a few more leap seconds? Maybe we need 2 leap seconds in a year, in a given year, depending on how the Earth is rotating. How are we going to decide how to do this, or are we just going to live with leap seconds forever? Well, the International Telecommunication Union was set up by the United Nations, and it has been considering for quite a while whether or not time signals should continue to have leap seconds inserted. We've been doing this since 1972. It's been working for the last 50 years, but do we want to continue with this rather ad hoc way of defining time? They were tasked with coming up with a decision by the UN. In 2015, they made a decision, an absolutely monumental decision as to what to do about the leap second problem. They decided not to decide anything until 2023. They basically said, we need to think about this some more. This is now no longer just a problem of thinking about how clocks work. With global finance and other things that really do depend on nanosecond accuracy, we have to decide what we're going to do about synchronizing clocks. And we've got a few years to think about it. So the answer is, we don't know at the moment. So I've told you how motion divides time. I've told you about how seconds are defined and what can happen in 1 second, to give a bit of context. I've told you how the Earth is slowing down and why it's slowing down, and the consequences of Earth slowing down are apparently the need for a leap second. Whether they will continue in the future, we will see perhaps in a few years' time. Thank you all for listening.